Welcome everyone. My name is Ricardo Camacho and thank you for attending this presentation on test verification principles and practices of ISO 26262 parts 4 and 6. My good friend and colleague Miroslav Zielinski, Director of Product Manager at Parasoft, will be presenting with me today, and we hope to take you through a very informative journey on compliance and software verification and testing in the automotive industry. To start things off, I'm going to very lightly touch on some of the standards that influence not just the development of software, but also the verification of the software that is being developed. Again, I will only be able to just skim through these standards as we don't have the time to go into depth, but I'm hoping to get the key points across. I'll then dive into a little more specifics on software verification by very lightly going through ISO 26262 parts 4 and 6. Merrick will then take us through some real life and best practices of software testing and automation in the automotive industry. Continuous compliance, automation, so around CI/CD, and there are some very informative customer use cases that Merrick will be taking us through. So let's start with some of the standards that contribute to software verification and validation. There's lots of automotive functional safety standards out there today. You've probably heard of international organizations like ISO, IEC, SAE, and others. You also have organizations like MISRA and AUTOSAR that contribute to the development of software that is safe and secure through defined coding guidelines for C and C++. Now, these standards provide best practices of development and verification of software at various phases within the development process. So you're going to see a common theme across these standards, and it's the V model. The V model represents a set of phases that are recommended for the development of safe, secure, and reliable software systems. The V model represents a process describing what to do, but not how to do it. How to implement the process comes in the form of selecting a development methodology. You can choose from an agile methodology like DevOps or a methodology like the waterfall approach, and there are other approaches like a spiral approach and so forth. All right, let's start with ISO 26262 and focus on the clauses that address software development and verification. ISO 26262 is subdivided into 12 parts, and the standard has been evolving since its first edition back in 2011. The standard's core contribution is offering a process and life cycle in developing hardware and software for automotive electronic systems. You will notice the famous V watermark in the image, which covers the life cycle, starting from development phases such as concept, then to managing requirements, then to design, then to implementation, then to testing, and then to maintenance and end of life. If you have been doing systems engineering, you are very familiar with this process. Now, Part 9 is very important to the verification of software because its purposes is in assigning a safety integrity level to the software unit. This level is used to recommend or highly recommend additional testing methods when it comes to verification. It's important because it can impact an increase in labor and cost in performing your software testing. Since the core topic of this presentation is software verification, I will be diving into part 4, which covers the product development at the system level, which also includes testing. You will see a horizontal line, systems and item verification. Coming from the right side of the V, part 4, clause 7, to the left, technical safety concepts. And you continue to see this horizontal lines connecting the right side with the left side as you look down the V. An important message here is that at each phase of development, systems, the design phases, and implementation, you need to also develop test cases at each of those phases. You're testing the system at different levels of abstraction to ensure a safe, secure, and high-quality reliable software system. You're going to see this common theme across other standards. What you're seeing here is the Automotive Software Process Improvement and Determination Process Reference Model Diagram, ASPICE. In order to ensure software safety and cybersecurity, it does not lie just within the technical engineering aspects of the development of electronic system. It requires the organization to incorporate processes and checks. with ways to also track and monitor progress within all practices of the organization in order to ensure that safety and cybersecurity practices have been adopted and safety and cybersecurity requirements are being satisfied. When it comes to ensuring that all requirements are being satisfied, requirements traceability is a must. Test cases from the right side of the V will link back to requirements, and commonly a traceability matrix is auto-generated, which easily identifies gaps in development of requirements and also with any missing test cases. Organizations also need to produce all the necessary reports to track safety and security compliance progress, and having a proof is key to ASPICE. So in general, ASPICE provides a measurement framework for independent assessors to evaluate an organization's capability for its software development, which is one of two key certification criteria for WP29 on organizational cybersecurity capability. And I'll cover this later in one of the slides. ISO 21448, also referred to as SOTIF, Safety of the Intended Functionality, provides additional guidance on design and verification validation phases to help assure safety of unthought of situations. For example, your vehicle inadvertently shuts down while you're driving it because of some initiated ADAS software update. Functional and situational awareness is critical to safety, especially due to the rise of complexity in all of these connected ADAS systems, with many sensors, including the use of artificial intelligence. So SOTIF takes into consideration sensors' limitation, decision algorithms, and intentional or unintentional misuses. It looks at the existing intended functionality and helps analyze and prevent the misuse of that functionality where it creates an unsafe scenario. Test cases will need to be implemented to address these unthought of situations that are flushed out. SAE J3061, originally published in 2016, is a vehicle system cybersecurity standard which relates security and safety processes to each other. J3061 defines a complete lifecycle process framework that can be tailored and utilized within each organization's development process to incorporate cybersecurity into vehicle electronic systems from concept phase through production, operation, service, and decommissioning. You can clearly see it here in the V model. And you can see on the right side the verification or testing that needs to take place to address the identified cybersecurity vulnerabilities. Traceability from test to requirements is also part of this. Now, IEC 21434 is intended to cancel and supersede standard SAE J3061. It differs from J3061 by decoupling safety. So the focus in 21434 is strictly on security. It addresses security within the entire life cycle, starting from the concept phase to product development, to production, to operation, and to maintenance and decommissioning. You can see the spiral on the left, and you can see the V model on addressing development and verification on the right. So again, you have testing to do to verify and validate your security requirements. One very important aspect of this standard is that it describes methods to determine the extent to which a driver or road user can be impacted by a threat scenario. These methods and their work products are collectively known as a threat analysis and risk assessment, TERA. It also defines cybersecurity assurance levels, mirroring that of automotive safety integrity levels, and describes the various software cybersecurity testing methods to apply to the code based on the cybersecurity assurance level, as you can see in the table on the right. It's also important to know where requirements and testing to requirements come from. They don't just come from your customers or standards or flushed out during development. They can also come from government agencies. The Unified National Economic Commissions for Europe, UNECE, released regulatory requirements on June 23, 2020, where they outlined new processes and technologies that automotive manufacturers must incorporate into both their organization and vehicles. And these regulations also apply to Tier 1 and Tier 2 suppliers of software and hardware components and mobile services. Today, automotive systems expand beyond the embedded domain, and now it includes networks with web applications, APIs, user interfaces, and programming languages like Java and .NET. This is just a very small sample within the WP29, but note the possible threats column and the mitigation and verification that will need to be performed. So testing must be done to show that these regulatory requirements are being satisfied. Now going to get into more detail regarding the different methods recommended for the verification of product development in ISO 26262. As I mentioned earlier, Part 4 addresses development and verification at the system level. Part 6 at the development and verification of the design and implementation phases. Within Part 4, you have clauses 6, 7, and 8. Clause 6 focuses on incorporating safety and development. Clause 7 on integration and testing, and Clause 8 on validation, all at the same phase of development. Table 1 shows recommended safety analysis methods for system architectural design. Deductive analysis and inductive analysis are listed. And based on the ASO level, the O represents no recommendation, the plus represents recommended, and plus plus is highly recommended. Deductive analysis is about knowing the safety aspects of a system failure, so the focus is on identifying the possible causes. Then one can address these possible causes to mitigate the safety concern. Fault tree analysis is an example of this type of analysis. Inductive analysis is about knowing the cause of a system failure, but focusing on identifying all the possible effects. Failure mode and effects analysis is an example of this type of analysis. Both of these methods will flesh out system-level functional and non-functional safety requirements. Table 2 lists the recommended methods for verifying these requirements. You have inspection, walkthrough, simulation, prototyping, and more. Probably noticed the OMG SysML logo. SysML modeling can help you model and simulate the collaboration between system of systems or just a system and its subsystems. Also, through simulation, you can verify behavior and identify gaps in the system design. Note that Table 1 is the left side of the V and Table 2 is the right side of the V. We don't have the time to go into all the details, so I'm just going to sum up some of the additional verification methods. Table 3 shows methods used in deriving test cases. You have analysis of requirements, interfaces, boundary values, and much more. Very important is field experience. The many years of knowledge and insight by the team is immensely valuable. I also listed a collection of recommended testings to be performed at the system level. You have fault injection, performance testing, requirements-based testing, stress testing, and much more. All the test cases created would all be linked to system requirements that they verify. I'm going to quickly cover Part 6, product development at the software level. Table 1 lists a set of best development practices or topics recommended in the development of software. If either using modeling or coding languages, you need to consider enforcing low complexity in models and code. Use of language subsets, use of defensive implementation techniques, and you can see here there's more listed. Table 2 for the software architectural design, it lists notations such as the use of natural languages and modeling languages like Simulink, Stateflow, and UML. Verification can then come from the analysis of the code through static analysis solutions, and for modeling from the execution of models. I'll actually show an example of this in a couple of slides. Table 3 lists a collection of principles to use in the development of the architectural design of the software, such as building a hierarchical software design structure, restricting the complexity, the size, and the interfaces in the design, and much more. Verification methods are listed in Table 4. Testing methods like static analysis, dynamic analysis, walkthroughs, or peer reviews, and more is recommended. Table 5 lists notations like Simulink, Stateflow, UML, and others that are commonly used. Just in case you're wondering how to simulate behavior of a system or systems of systems or down at the software design and architectural level, I have a short video to show you in the next slide. This is an example of a power window controller simulation. Simulink is used to build the control logic, and the code that it produces will ultimately be used in production. In this example, the Simulink model has been integrated into a UML model, and where you can integrate the driver, the window, the actuator, and more if desired. Because you get to execute the model, you are therefore testing the design, and in this case, also the code. Table 6 offers a list of design principles. No recursion, no unconditional jumps, no implicit type conversion. All variables should be initialized, and much more. On the verification side, you have walkthroughs, pair programming, requirements-based testing, which is realized through unit testing. And many more methods are listed. You also have static code analysis, data and control flow analysis, and there are several coding standards that can be applied. CERT for security, MISRA, AUTOSAR C++14, and we have customers that we have helped create their own coding standard. Not only do they apply it within their own organization, but they also require compliance from their suppliers. This is to ensure a common level of software quality across the entire supply chain. Table 9 lists the recommendations for ensuring completeness of testing. Code coverage is a way to achieve this. In a nutshell, structural coverage is the identification of code that has been executed and logged for the purpose of determining if the software has been adequately tested. The coverage methods recommendations are based on the safety integrity level. You have statement, branch, and at the higher levels of concern, for safety, modified condition decision coverage, MCDC. For MCDC, branches can grow in complexity where there are multiple conditions in a decision and every condition must be tested independently. During the design phase, you will have requirements that traverse multiple units that fulfill desired functionality. Testing of these units integrated together to verify the requirement needs to be performed. Integration testing can take the shape of multiple units being tested together. Remember, based on the abstraction level of product development, integration testing can also take the shape of multiple components being tested together. Other test methods can be applied to these integrated software parts, like call coverage, fault injection, boundary value testing, and much more. Clause 11 of Part 6 is all about the physical test environment. Simulation does not require costly hardware or other physical components to be available. Simulation cuts costs, saves time, but testing on the actual target is a must. You'll see that table 13.1a has hardware in the loop, the networked ECU, and the vehicle itself. Verification of the software and the target hardware is crucial. The actual table is not shown in this slide, but table 14 recommends requirements-based testing and fault injection testing to be performed. Table 15 recommends various analysis methods to deriving test cases. Now that concludes Part 6. To bring it together, these standards offer a lot of experience and strategies to an organization in what the development and verification of software should consist of. There are many safety and security software development best practices provided, which constitutes the left side of the V, and in turn, many best practices in the verification of software to ensure that it's safe and secure, the right side of the V. Both should be addressed at each phase of development because you have different levels of abstraction. Therefore, you also have various testing methods at different levels of abstraction. However, these standards don't tell you how to perform your testing. So I'm going to pass it over to Mirek, where he will be presenting on modern software development workflows that automate development of test automation and compliance. Okay, I'm going to pass it over to you, Mirek.
Thank you, Ricardo, for the excellent overview. So, as we can see, to provide safe, secure and compliant software, automotive teams face the challenge of implementing multiple testing techniques without killing productivity. Productivity, which is so important these days because of the cost of qualified developers. So, how to cope with this challenge? The answer is, of course, automation. Automotive software teams require automation to stay productive with large code bases and growing requirements for compliance testing. And automation of software testing and compliance enforcement is a vast subject, and our time today is very limited. So I will only touch upon a couple of essential aspects and share with you some of our high-level observations. And the first thing is software testing for compliance needs to be a part of this, and it needs to be continuously enforced. Most of the teams use some CI in their development process these days, and compliance testing needs to be integrated into automated pipelines for effective enforcement. Compliance requirements must be codified and stored with the source code and enforced automatically with the tools in the pipelines. And this of course requires software testing tools that can be fully automated and easily configured. Heavyweight IDE-centric tools are not easy to automate, and they do not perform very well in continuous integration-based workflows. For the high level of automation, lightweight command line-based tools configured with human-readable text files are strongly preferred. And of course, tools need to support containerization. It's hard to stress enough how helpful containers are in building automated and scalable pipelines. Containerized toolchains, among many other things, help in assuring unification of the development environment, faster reactions to security problems, and also containers make it very easy to track versions of our toolchains and manage them, which is very important from the tool qualification point of view. And finally, we have a subject of integrating compliance testing with the modern development work, which is correlated with CI integration. And the modern workflows are characterized by a very dynamic approach to branching and merging, and close integrations with the CI/CD platforms such as GitHub, GitLab, or Azure DevOps. Developers typically create short-living branches to do their work, and once they are done, they create pull or merge requests to integrate the code with the stable stream. And the feedback regarding compliance shall be an inherent part of these workflows. Developers need to see static analysis results, unit testing, and code coverage results in the CI platform, correlated with their activity in the SCM. And the diagram here presents a simplified workflow. When starting work on a new functionality or fixing a problem, a developer creates a branch, say a feature branch, and continues working in this branch until the code is ready. And there are many strategies for working with branches, and teams use different naming conventions, but this simplified diagram captures the essence. And once a developer is ready with their code, they create a pull or merge request that triggers the CI pipeline. And the pipeline contains various testing actions, including testing against compliance requirements, which serve as a quality. And this is a high-level schema we have known for many years. What is new is the growing importance of the compliance aspects in the quality gates. What we can see in this slide is, as I said, simplified. In the real-world scenarios, branching diagrams are more complicated, and teams may use several different configurations of the quality gates. For example, in the early phases of the development, the quality gates may be relaxed and focus only on the things that may be expensive to eradicate later. So, for example, we may want to enforce only a subset of the coding guidelines, and we may not be very strict with the code coverage levels. This approach aims at avoiding expensive requirements for the prototype code that may be thrown away. But once we move closer to the production/integration stream, the requirements become tighter and quality and compliance gates become more difficult to pass. And depending on the situation, the quality and compliance gate in the pipeline may static analysis with safety and security coding guidelines, automated verification of software architecture and components interdependencies, data and control flow coupling, and naturally unit integration and system level tests if only possible with mandatory code coverage. And all these testing methods are automated in the pipeline with software testing tools. Tools that are containerized, configure themselves automatically by reading the files, configuration files stored together with the source code. Let's see this from the other perspective on another diagram. Our story here starts with a developer pulling the code from the Git repository. And source code includes infrastructure, toolchain, and pipeline definition files. So the development environment, including the testing tools, is automatically provisioned with containerized tool chains according to those definition files. So compiler, build system, static analyzer, unit testing framework, and code coverage tools are all distributed in containers following these definitions in configuration files. And once the developer locally tests the code, it is pushed to the repository, which triggers the CI pipeline. And here again, the development environment is dynamically composed using containers. The same containers are used for local development and pipelines, which assures consistency between developers' desktops and the CI/CD nodes. And when CI/CD pipeline executes, it goes through the quality and compliance tests, fail the pipeline, and block the quality gate in case of failed requirements. And the information about failed tests is delivered back to developers for remediation. And once developers fix the problems, the code is integrated with the stable stream. And test reports and compliance documentation is dynamically generated in the pipelines and made available for audits and certification process in an offline and online form. And again, this diagram is simplified, but it visualizes the main idea. In our conversations with the automotive software development teams, we see these concepts being widely adopted. Most of the teams that we have conversations with are either already very advanced in automation of their testing and continuous compliance, or are planning to invest in it soon. Okay, so these were some high-level observations about compliance testing automation that we wanted to share with you. And in the last part of our presentation, I would like to present two examples of customers who were facing interesting challenges related to automation of their workflows. And the first customer represents a new wave of electric car manufacturers. Their software teams have already adopted a very modern approach to software development. They have a dedicated DevOps team responsible for workflows and tool chains. And developers' productivity is their focal point. And what is special about this organization is that all testing and safety, security, compliance is fully automated and enforced in the CI/CD. From the very beginning, they intended to have 100% CI/CD based workflows, which among many other benefits simplifies new team members onboarding and to some degree paves the way to continuous compliance. And from the technology point of view, their development stack is pretty much standard. Depending on the project, they use GNU GCC or Tasking cross compilers. They are very experienced with Docker and Kubernetes, which are used for scalable pipelines. For CI, they use Bitbucket and Git. And from the operating system's point of view, they use either SafeRTOS or Linux with Yocto. And their goal was to implement MISRA C 2012 compliance for all the projects and have it enforced entirely in the CI pipelines with a very short feedback delay. The general expectation was that developers should get a complete set of static analysis results within several minutes after pushing the code. And scale of this deployment was the main challenge. They are working on 3 dozens of different ECUs, and each of ECU has several variants, which gives in total almost 300 variants. So every change introduced to the common code base may trigger up to 300 pipelines. And on average, they have 70,000 plus pipelines executed per day. And what was achieved is that every pipeline now includes MISRA C 2012 quality gate. MISRA compliance results generated in the pipeline are compared against the baseline results, and developers are notified only about new violations relevant to their most recent code changes. And results are injected to the Bitbucket and sent to developers via email. And everything happens within several minutes after the check-in. And with this customer, even though the initial requirement was relatively simple, the scale of the deployment and desired level of automation was a big challenge. Their CI is entirely in the cloud. All toolchains are containerized, and the infrastructure is defined as code. So the CI bandwidth automatically scales up and down depending on their current needs, providing them colossal flexibility. And the second interesting example I would like to share is a semiconductor software and services provider. They are expanding now in the automotive market and provide specialized SoCs for ADAS and autonomous driving. And when they approached us, they had limited experience with functional safety. Their product is a complex system on chip developed as a safety element out of context. The product includes hardware and software, and it's developed to meet ASIL-B of D requirements, and it comes in a different configurations depending on a specific OEM requirements. And their technology stack is difficult to describe in one slide. There are more than 50 software components included in the SoC. Some of these components are developed exclusively for their main product, and some are shared with other products. And their development teams are distributed across the globe. So various technologies and tools are used in their development. The interesting thing is that in addition to publicly available compilers, compilation toolchains, this customer is also using a homegrown compilation tools for their custom CPUs, custom processors. And they had two goals they wanted to achieve with the software testing tool vendor: implementing MISRA C 2012 compliance process and introducing code coverage metrics for various testing practices like unit integration and system level testing that were already in place in their organization. And the main challenge that we were facing was the diversity of their development environment. As I already mentioned, the product includes multiple hardware architectures and around 50 software components. And software runs under the control of multiple operating systems. And of course, CPUs communicate with each other. And some software components are developed internally, and third-party companies provide some. And to complicate it even more, some components are based on custom hardware architectures, and as I already mentioned, they are programmed with compilers developed in-house. And our customer was looking for a testing tools vendor that can provide both static analysis and code coverage toolchain that is certified for ISO 26262 to eliminate the effort for tool qualification, supports as many of their development environments as possible, and is ready to extend the product to cover their custom architectures, compiler, and complex embedded setups. And by cooperating closely with us, our customer was able to build a sound MISRA C compliance process and add code coverage metrics to majority of their testing activities. And all the testing results are collected in the central reporting system, which then serves as a source of information for compiling customer-specific reports that reflect the actual configuration of the SoC that has been sold to the specific customer. And working with this level of diversity in the development environments, trying to unify it was a huge challenge for us. But we really enjoyed participating in building cutting edge technology. And this, I believe, concludes our presentation. Handing back to you, Ricardo, for a quick summary. Thank you.
Well, thank you, Merrick. That was a great presentation on how software testing is being realized out in the automotive industry and out in the trenches of the real world. So to sum things up, we very lightly covered what the standards offer and recommend in the development and verification of software systems. Merrick then dived into how software verification validation is being realized through modern development workflows, such as automating static analysis, unit testing, integration testing, system testing, and code coverage into the CI/CD pipeline. He also touched on containerization and many other tools that work together in a DevOps solution. Anyways, I hope you found this presentation very informative. I know we covered a lot of content in a very short amount of time. Okay, so we're going to open things up for Q&A, so please enter your questions. We have a couple of questions right now. Does your tool integrate with Microsoft Azure DevOps? Absolutely. In fact, most of our customers or prospects are looking for test solutions that work within their CI pipeline. So we have integrations not just with Azure, but tools like Jenkins, GitLab, GitHub, and others in support of your custom workflow or CI/CD pipeline. Docker containers, for example, is another solution that we are integrated with. And we are actually available on Docker Hub, so that's really interesting. Now, one other question, is it possible to try out this integration before buying it? Yes, I actually recommend that you go to our website, parasoft.com, and on the top right of most of the web pages, you'll see a Contact Us button. There you can reach out to us for anything you need. And you're also going to see a Try Parasoft button. The Try Parasoft button will take you to a page where you can request a demo. And there is also a quick overview link that will take you to a simulation tour of our C++ test product. Okay, I don't see any more questions. Thank you, everybody, for attending our presentation. And we have lots more of these webinars that we do. So check us out on the website for other presentations that are coming up. And thank you. This concludes our presentation. Bye-bye.